the the topics that are how much energy can be stored in inductor, how the current is increased, or how the current decay is occurring in the inductor. So let us take first example. In this example, a coil, that is a inductor, having a resistance of 10 ohm and a inductance of 4 Henry is switched across a 20 volt DC source. So it is same circuit that we have used in analysis. So what we have to do now? We can understand that a 20 volt DC battery is connected with R and L. What is the value of R? Value of R is equal to 10 ohm and the value of L is equal to 4 Henry. So what we have to calculate? We have to calculate that how much time is required by the current to reach 50% of its final steady state value. And second, we have to find out what will be the value of current after 0.5 second. That means if we are increasing the current in a RL circuit, if we are increasing the current exponentially, then what will happen? If we are increasing the current, for example, the RL circuit is connected with a battery. Here the battery voltage is 20 volt. So if we are connecting this circuit with a battery that is 20 volt, then what will happen? The current will get decreased after some time. So we have to find out that how much time it will require to reach the 50% of its final steady state value. And what will be the value of current after 0.5 second? If we switch on the circuit, then we should know that after some time there will be some current that will flow in the circuit. Okay, so here in the example it is asked that after 0.5 second how much will be current that will flow in the circuit. So how you will solve it? To solve this circuit, first you should find out how much current that is increased. As we know that the rise of current through an inductive circuit is find out by putting the equation I is equal to I, that is maximum in bracket I minus e raised to minus t divided by lambda. So if we are rewrite the equation, then what we can write? We can write down this e raised to minus t by lambda as a main, or in another word we can say that this I is put up in this side and this one is also put up in this side. So what will be the equation? Equation will become e raised to minus t by lambda is equal to I minus small I divided by 1, or another word we can write it as a I divided by e raised to e divided by t into lambda. So taking both side logarithm, so what will be the equation? It will be 1 by lambda into log e, and the right hand side it will be log here log in and it will be I by 1 minus small I. Now what you need to find out? You need to find out how much will be the current after 0.5 second. So it will be, the equation will be again simplified. It will be RT by L is equal to Rn. Here it will be 1 divided by capital I minus small I. So let us put the value of L by R in the equation. So what is L? What is I is equal to V by R? So what is the value of V? This in this example the battery voltage is 20 volt. So it will be 20 divided by 10 and the resistance value is 10. So it will be 2 ampere. So putting the 2 ampere in this equation, we will get 4 by 10 into Im into 2 divided by 2 minus 1. So you will get 0.277 second. And now if you want to find out the time constant for after 0.5 second, after 0.5 second how much should be current? So you can find out lambda is equal to L by R. So what is the value? It will be 4 by 10, that is 0.4 second, and t is equal to also 0.5 second is given. So putting this value, that is 4 and 5, in this equation, you can find out the current, that I is equal to 2 in bracket 1 minus e raised to minus t divided by 0.4. What is the value of E? Value of E is equal to 2.718. So putting the value, you can solve it. Now let us take the second example. In this example, a coil has a time constant of 1 second. That is, the time constant is given, and the inductance of 8 Henry is given. That is obviously a self inductance of a inductor. Now, if we are connecting this coil with a 100 volt DC source, the current will flow, but how the current will get increased? That is, you have to find out the rate of rise of current at the instant of switching. That is, if you are connecting R and L with a battery, and if you are switch on the battery, so what will happen? The current will flow. That means it will increase exponentially. That means you have to find out how much rate it will rise. The second component is that you have to find out the steady state value of current, that up to how much time it will increase. Up to some time duration it will get steady. So you have to find out how much is the steady state value of current. And last thing, you have to find out how much time is taken by current to reach the 60% of its steady state value of current. So how you will find out? In this data, you are given the time constant, inductor and the battery value. So first you can find out lambda is equal to L by R. So by the equation you can find out the resistance, because R is equal to L by lambda, and the value of L is equal to 8 and lambda is equal to 1, so it will be 8 ohm. Now at initial condition, it will be di by dt is equal to V by L. That is, what is V? It is 100 by 8. So you will get the current, that is 12.5 ampere per second. That means per second this 12.5 ampere will get increase in the circuit. So how much is the steady state value or the maximum value? Maximum value you can find out by putting the equation Im is equal to V by R. As you know, the battery is 100 volt rated and the value of resistance is 8 ohm. So it will be 12.5 ampere. Now 60% of 12.5, what is it? It is 7.5 ampere. So putting this in the equation, it is I is equal to Im in bracket 1 minus e raised to minus t by lambda. So what is I? Now I is equal to 7.5. What is the maximum current? 60% of the 12.5 is 7.5. Now what is maximum current? It is 12.5. So putting this value, you can find out the current. So what is the current? It will be 0.915 second. That means this is the time up to which the current will get maximum value, or it will get the steady state value. So these are the three values that we have got. Now let us take a third example. A DC voltage of 80 volt is applied to a circuit that is containing a resistance of 80 ohm in series with a inductance of 20 Henry. You have to calculate the growth of current at the instant of completing circuit. And you have to consider, when time is equal to 0.5 ampere, what will be the current or the time constant. And third, you have to say for the condition I is equal to 1 ampere. So the voltage equation for the RL circuit, as we know that it is V is equal to IR plus L di by dt. So if we are putting this V in the right hand side, then it will be L di by dt is equal to V minus IR, or it is di by dt is equal to 1 upon L in bracket V minus IR. So when I is equal to 0, at that time what will happen? The rate of change of current di by dt is equal to 1 upon L, and the value of current is 0. So the maximum current, we can say that it is 4 ampere per second. Now when the current is 0.5, that is current, if we are doing the half of the current to the circuit, then what will happen? The rate of rise of current, that is di by dt, we can put the value in this equation. So we can find out that it is also get half. Now for the case when the current is 1 ampere, the rate of change of current is equal to AT minus LT multiplied by 1 divided by 20. So it will get 0. So in other words, we can say that current has become a steady at 1 ampere. Let us take the last example of these circuits, of this electromagnetic circuits, or the last example of this chapter. A DC current of 1 ampere is passed through a coil of 5000 turns and it is producing a flux of 0.1 milliweber. You have to calculate what will be the inductance of a coil and what would be the voltage that will be developed across the coil if the current were interrupt in the 10⁻³ second. And the last thing you have to find out is that how much energy is stored in the inductor. So 3 things you have to find out in this example. This example was asked in the GTU exam of January 2010. So it is very much simple example. You have to first calculate how much is the how much is the current, right? How much is the inductance of a inductor. So which are the data that are given? The data given are like this: I is equal to 1 ampere, N is equal to 5000 turn, phi is equal to flux, that is 0.1 milliweber, and dt, that is the rate of change of time, is equal to 10⁻³ second is given. So how to find out inductance? Inductance we know already that L is equal to N phi divided by I. What is N? N is the number of turns. The coil is having 5000 number of turns. And how much flux it is developed? It is developing 0.1 milliweber. So we have to convert it into Weber. So milliweber into Weber we can convert by multiplying 10⁻³ and the current value is 1 ampere. So by putting this value we can find out the inductance of the circuit is 0.5 Henry. Now by this inductor, how much EMF will be induced? It will be induced the EMF as per this equation, E is equal to L di by dt. So what is L? L we have already found, that is 0.5 Henry. So putting the value of L, and we know the di by dt, it is 1 divided by 10⁻³. So putting this value we can find out that EMF that is induced is 500 volt. Now the question is that how to find out energy that will be stored in the inductor. So which equation you can use? You can use the equation energy stored is equal to 1/2 Li square. So 1/2 into L is equal to 0.5 Henry and the value of current, that is 0.1. So we can find out the energy that is stored in the inductor is equal to 0.25 joule. Now we will see the last topic of this chapter, that is the force experienced by a current if your current carrying conductor is placed in a magnetic field. So force on a current carrying conductor in a magnetic field can be defined as when a current is passed through a conductor, a magnetic field is obviously produced, right? So when a current carrying conductor is placed in a magnetic field, what will do? It will interact with any other magnetic field and produces a force. That force is equal to F is equal to BIL, where F is the force produced in newtons, B is equal to flux density, I is equal to current in ampere, and L is equal to length of wire in the field. So where this concept is used, let us see. When a current carrying wire that is free to move is placed in a magnetic field, this one is the wire. If we are putting free in the magnetic field, what will happen? It will experience a force and the wire will jump out the field. The production of this force is known as the motor effect, because this force is used in the electric motors. So now you can say that by this principle the motor is working. So Fleming's right hand rule can be say that we use Fleming's left hand rule to find out how much is the force that is developed. If the thumb and the first two fingers of the left hand are placed comfortably at the right angles to each other, we have already seen this law, that by this law, when the first finger pointing out the direction of field, second will pointing out the direction of current, and the third will show us, that is thumb will show us the force that is developed in the current carrying conductor placed in a magnetic field. So which are the points that should remember when applying this rule? First is that the direction of the field is from N pole to S pole. The direction of the current is from positive terminal to the power pack to its negative. That is conventional current direction. The third is that the rule applies only where the current field direction are at the right angles. That means if you are considering these two magnets, and if you are putting this current carrying conductor that is placed in this magnetic field, if you are putting it, then it will be a magnetic field. So this conductor carrying current will be in the out of screen, that is in this position. Now if we are putting this current carrying conductor in the position that is in the magnetic field, then what will happen? It will experience a force, and that force will be in the magnetic field and the current carrying conductor into the screen. So into the screen force says that this is doing a